it is known as the LVDT as a secondary transducers. Okay, so that converts to low displacement voltage. So similarly, that in case of capacitive transducers also, it is also known as the secondary transducers because it's varying the distance between the plates. Okay, so distance between the plates, moving the plates, that you can calculate the output electrical voltages. Okay, so that is when working of the capacitive transducers. Okay, the same thing happens also in this case. Okay, so actually that capacity, that the basic workings of the capacitive. Okay, what is the capacitors? That is already that you know. What is the capacitor? Actually, you know that there are two connecting plates. Okay, so there are two parallel, the connecting plates are there. Okay, so basically, what is connecting plates? Because it can, stores the charge or stores the energy, whatever. Okay. So now, suppose this is the dielectric materials in certain materials like air, liquid, or whatever. So dielectric materials, So basically, it separates. These two plates are separated by this, dielectric mediums. Okay, these are dielectric mediums. Okay. So now, if you suppose some give supply. Okay, suppose if you give some supply across these two plates, then what will happen? So obviously, you know that the charge will be accumulated. Okay, it will be accumulating across the plates, and that will be stored. Okay, so that will be stored. Okay, the charge will be accumulated across the plates, and accordingly that so it will be stored. So that is the function of the capacitive, is the capacitance. Okay, so now actually this the capacity, this energy storing capacity, or capacitance, that is the function of charge, the capacitance. Okay, so basically so that is equals to what? So that is equals to epsilon, that is epsilon a that is divided by d. Okay, that is the formula. So C equals to that is the epsilon a by d. Okay, so here you can see. So this is the C equals to so that is the epsilon a by d. So C equals to what? So epsilon means A means what? A means actually overlapping area. Okay, so A is actually overlapping area. Okay, overlapping area of the plates, and D basically distance between the plates. Epsilon is the permittivity of the medium, and epsilon r, there's a relative permittivity. Epsilon 0 is the permittivity of the free space. So actually epsilon, that we can write that epsilon equals to epsilon r into epsilon 0. That is the product of the relative permittivity, and that is the absolute permittivity. That is the permittivity of the free space. Okay, that is a free space. Okay, so now actually what is happening? So C equals to that epsilon a by d. Okay, so d is the distance between these plates. Okay, so here we can see that if the distance varies. Okay, suppose if the distance increase, if we increase the distance between the plates, so capacitance will decrease. Okay, capacitance will decrease. Okay, so if we increase the area, okay, if we increase the area, or if we increase this dielectric medium, so you can see the capacitance, changing capacitance, that increase. Okay, increase capacitance will increase. So basically this change in capacitance, that is changing capacitance, that is depends on that is three materials. One is that change in the dielectric constant. Okay, variation in the overlapping area, and variation in the distance. There are three main points. Okay, so change in capacitance, that is depends on the three parameters. One is that variation in dielectric constant, change in dielectric constant, medium, change in overlapping area, and change in distance. Change in distance. So first thing is that what is actually change in area? Okay, change in area means suppose suppose that there is a plate. Okay, suppose this is the plate. Okay, there is a parallel plate, So this is your parallel plate. Okay. Suppose if we this is the top, this is the top plate and this is the bottom plate. Okay. Okay, this is the top plate and this is your bottom plate. Okay. So this is actually, there's some overlapping area is there. Okay, this is an overlapping area is there. Okay. Suppose I am drawing in this way. This is better to understand. Suppose this is the plate. This is one plate. Okay, this is the one plate. Okay, this is the plate and another overlapping. So suppose another plate is there. Okay, suppose this is the another plate. Okay, so this is the another plate, right? So this is the another plate. So this is the actually overlapping area. So this is the overlapping area. Okay, suppose this is the area. This is the overlapping area, and suppose this is the x is the width. Okay, so this is the x, that is your width. Okay, x is the width, and suppose the L is the length of the plate, so that is your constant. So that is a constant. Okay, that is a constant, and x is varying. X varying. Okay, so now the C equals to what we can write here. C equals to what we can write here. Epsilon into A. A means area. So area of what you can write, that is L into x. Okay, L into x by what? L into x by t. Okay, so C equals to what? C equals to what? Epsilon into L into x by t, right? So now actually in this case, so in this equation, what we can see in this equation, so epsilon is a constant. Epsilon is a constant. Okay, length is a constant, means your length is a fixed. Okay, length is a fixed, and d, that is a distance, is a fixed. Okay, so distance is a fixed. So what is changing? Changing, that is the x. X is varying. X is varying means if we move this plate, move this plate linearly. Okay, if we move this plate, linearly. So if we move this plate linearly means what? So x will be varying. Suppose suppose if this plate is moving in the left side. Okay, so overlapping area here. So this is the overlapping area. This is the overlapping area. Suppose if we move this plate in this side, so overlapping area will increase or overlapping area will decrease. Okay, so that depends on the yes.
So the area will decrease.
Yes. That means that is increase or decrease. Okay, the overlapping area increase or decrease by moving the plates. Understood? So the overlapping area that will increase or decrease. Okay, so by changing the area by plates. Okay, so actually, so x is varying. We are varying the x. Okay, we are varying the x. Right. So that's why the C equals to the equation that epsilon into L into x by d. Okay, so now the L and epsilon d are constant, so we can see in this from this equation that we can write here that C proportional to x. मतलब जितना डिस्प्लेसमेंट होगा, जितना डिस्प्लेसमेंट हम करेंगे x का वही हम चेंज करेंगे, ठीक है? पर ओवरलैपिंग एरिया चेंज करें, चेंज इन ओवरलैपिंग एरिया that is proportional to the change in capacitance, the change in the capacitance. Okay, if you can see that in case of strain gauge, strain gauge activity, that we have seen that already, that what was the input quantity? We are giving some pressure, we are giving some temperature of force in the strain gauge, we are giving some temperature input quantity in the activity. So in case of strain gauge, what happened? The strain is developed. The strain is developed, resistance. Okay. So in case of activity, what we have seen? In case of activity, due to change in temperature, the resistance value changes. Okay. So now, how we can measure it? We have configured with the Wheatstone bridge circuits. Okay, we have configured with Wheatstone bridge circuits. So now the bridge will become unbalanced. So accordingly, that we can measure the output voltage. Similarly, in case of the capacitive transducers also. So what is the input quantity? What is the input quantity? The displacement. Okay, displacement. The input quantity. Okay, so displacement that causes the change in capacitance. Okay, causes the change in capacitance, right? So now, like RTD and strain gauge, if we, that is, if it is capacitive transducer also, this change capacitance, if it is configured with any bridge circuits, Wheatstone bridge circuits, then what will happen? Displacement is the input quantity. Okay, so change in capacitance causes the change in capacitance. So obviously you can see that bridge will become unbalanced. Okay, so in that case also you can see bridge will become unbalanced. Okay, so unbalanced bridge, then we can vary the output voltage. So output voltage can be calibrated. Okay, in terms of displacement. Okay, like the RTD, like the strain gauge, the same principles. So you can configure also like RTD and the strain gauge in the capacitive transducer can be configured also with the Wheatstone bridge. circuits. Okay, so that is you can measure the change in capacitance. Okay, from the bridge circuits, so bridge will become unbalanced. Okay, so now we can measure the output voltages. Okay, the same principles happen also in the capacitor transducer. Same principle follow. Okay, so in this case, that the changing overlapping area. The first condition, that there is a changing overlapping area. So changing overlapping area means that area means L into X. So here actually the L is a fixed. We are changing. Suppose this overlapping area means overlapping area changes. Okay. So if we moving the plates, so overlapping area increase or decreases. Okay. Right. So now the C proportional to X. Okay. C proportional to X. Right. So now what we can write here. Suppose we are find the sensitivity. How to find out the sensitivity in the overlapping area? So we know that already you have solved the problem in the last class. The sensitivity means what? The sensitivity means changing output by changing input. Okay, sensitivity means what? Changing output by changing input, right? So here the change in output means what? What is your output? Output obviously is the C capacitance, that is the DC. Okay, change in output. Okay, and what is the input? Input that is the X. X is the input, means the overlapping area of this with X. X here is the input, right? X is the input, changing input, right? So now what is the formula? What we can write in this case? So we can write here that is DC. Okay, if we DC that divided by dx. So that means changing output by changing input. Okay, changing output by changing input with respect to x. Okay, so now what we can write? So dc by dx, that is equals to nothing but so the epsilon L by d. Okay, epsilon L by d. So dc by dx, the epsilon is a constant, L is the constant, d is the constant. So what we can write? dc by dx. So that is sensitivity is a constant. So dc by dx equals to constant. Okay. So now what we can write? Suppose this is equal to suppose this is equal to k. Okay, this is equal to k. Okay, it's a constant. Okay. So now what we can write? What we can write? dc equals to what? dc equals to what? That is k into this is equals to k into dx. Okay, dc equals to k into dx. So now in this from this equation that we can establish that one thing, dc proportional to dx. Okay, that is dc proportional to dx. So that means what? That means the change in capacitance that is proportional to the change in this overlapping area. So obviously it will provide a linear relationship if we plot the curve. This is your capacitance, this is your the displacement, this is the your displacement or overlapping area, whatever. Okay, so it will be showing a linear curve. It will be showing a linear curve because it is a constant and this dc that is proportional to dx. So this is the one characteristics of the capacitor transducer. This is the one characteristics. Okay, between the capacity and the displacement. Okay, so this is the first condition. So that is changing the overlapping area. So this is very simple explanation. Very simple explanation. Okay, so DC proportional to dx. So next thing is that suppose next thing. That is changing the dielectric, changing the dielectric medium. Okay, so changing the dielectric medium means, suppose changing dielectric medium, in this equation. First one is that variation in the capacitance transducer because of overlapping of capacitance plates. Okay, so first thing that we have explained. Second is the change in capacitance because of the change in dielectric constant. Okay. Capacitor changes because in the change in dielectric constant. So change in dielectric constant means suppose this is your capacitive medium. Okay, so this is the capacitance plate. So now actually what will happen? Suppose this is the free air because dielectric medium, so there is a free air. There is a free air. So when some we fill some liquid, okay, some will fill some liquid up to this level. Okay, some liquid is filled up to this level. Okay, so this is the free press. Okay, top the top portions of the above these liquid levels, that is the free space, and this is your liquid. There is a liquid. So obviously there is a different dielectric constant. Okay, there is a different dielectric constant there in between this. There are different dielectric constant. What is is a free air space, and also there is a liquid medium is there. Okay, so different dielectric constant means dielectric constant changes here. We have varied the dielectric constant. So in that case, we will be getting the different capacitance value. That is a C1 and that is a C2. So in this case, we will be getting some different capacitance value. Okay, that is C1 and C2. C1 for this one and C2 for this one. Okay, so total capacitance, we can write here. So that is, C1 plus C2. Okay, this is the total capacitance, that is C equals to C1 plus C2. So now you can, it is a pretty practical application. It is a practical application just using the capacitive transducer you can measures also, the level, level of the liquid in any storage tank or whatever. Okay, suppose there is a storage tank. Okay, there is a storage tank, so the capacitive transducer, that is inserted, that is mounted, that is fitted, okay, inside the tank. Okay, so that is in that case, that one wall will be acting as another conductive medium, another plate is another conductive medium. Okay, so that will be explained later in the experiments. You will be performing the experiments. Okay, so in that case you can you will see that when you increase the liquid level, when you increase the dielectric medium, the liquid level, between the capacitance, then what will happen? Then accordingly, the capacitance, this capacitance value, obviously it causes the change in capacitance, okay, and this capacitance value will increase. Capacitance value will increase, okay. So capacitance value will increase. So actually, what we mean to say? We mean to say that if we increase the dielectric medium, if we increase that, suppose your dielectric medium up to this level, your dielectric medium up to this level. Okay, suppose you will be getting some capacitance value 2 microfarad, 3 microfarad. Okay, suppose you will be increasing, suppose the that level increases, dielectric medium increases up to this level. So obviously, capacitance value will increase. Suppose 6 microfarad, 5 microfarad, 10 microfarad. Okay, so so that's why we can say that is change in capacitance. That is del C. So del C, that is proportional to change in dielectric constant. Change in the dielectric constant. So del C also that is proportional to the del epsilon. Okay, so that means what? If we increase the dielectric medium, if we vary the dielectric medium, okay, if we increase the level between these two conductive plates, then what will happen? Automatically the capacitance value increases. Okay, capacitance value will increase. Then we can calibrate the capacitance value and go through the indicator meter from the outside. Okay, so now this is the function. This is the change in capacitance. Means C equals to epsilon A by D. So C, that is proportional to the change in capacitance del C. So that is proportional to the epsilon into A. Okay, the epsilon into A. Next thing is the distance. Okay, suppose C equals to what? Epsilon A by D. C equals to what? Epsilon A by D. Okay, so now if we vary the distance, okay, if we change in vary the distance, so distance means here suppose means distance between two plates. Okay, so input quantity, what is the input quantity? In the change in input means what? Change in displacement, the distance. Okay, so now what we can write, if we see C equals to this equation, C equals to epsilon A, C equals to epsilon A by D. This is the equation. Okay, this is the equation. C equals to epsilon A by D. Okay, so what is the output now? Change in capacitance. That is output. What is the input now? Change in distance. Third measurement. Okay, change in distance. So now, what will be the sensitivity in that case? We can from it, that is C DC that is DD. Okay, DC that is DD. Okay, so now what we can write? DC DD, that means if we differentiate, then what we can write, that is equals to epsilon minus of epsilon A minus of epsilon A by D square. Okay, minus epsilon A by D square. Okay, so here the input quantity is present, that is in terms of D square, and minus epsilon by D square. So obviously you will be getting from this equation, a non-linear relationship. Non-linear relationship, which is second characteristic. Okay, the first characteristics, you have seen there is a capacitance and there is a displacement, there is a linear relationship. Okay, in case of the overlapping area, dielectric medium. Okay, but in that case, when you vary the distance between these two plates, okay, distance, this distance between two plates, when you vary, okay, will increase, then what will happen? The capacitance value will decrease. Okay, capacitance value will decrease. Okay, so it is the effect. That is the effect. Capacitance value decrease. So that will provide, from this equation, that we can say that it shows a non-linear relationship. Okay, it will shows a non-linear relationship. Okay, non-linear characteristics. Okay, when the distance vary, the capacitance value decreases. So there are two characteristics that we can design. That is, we can plot. There are two characteristics. One is that linear relationship plot, and another is that that is a non-linear plot. Okay, non-linear approach. Okay, so when we provide the linear response, so if we see suppose if we change in the overlapping area or change in dielectric medium, so changing capacitance will increase. Okay, so that is proportional. But here the inversely proportional. Inversely proportional. So that means it is a decrease. That is a decrease. So there is a non-linear relationship. Okay, so that is a non-linear relationship. Fine. So actually, this is the main working. That is a capacitive transducer. That is the main working. That is C equals to. That is the significance. The significance of this. Of this equation. So that is equals to C equals to epsilon A by D. That is the main significance. Okay, that is the main significance. Fine. So now next thing is that suppose there is some practical setup. There is some practical arrangement. That is a differential arrangement. Okay, that is a differential arrangement. Differential arrangement means suppose that thing you have to design, or you have to derive. Okay, derive the value of the capacitance. You have to calculate the value of the output voltage actually. Okay, output voltage. In case of LVDT, that you have noticed differential arrangement. Differential arrangement means that we will be getting some differential output voltage, net output voltage. That is differential output voltage. That is V equals to V1 minus V2. That is V2 minus V1. So that is a differential arrangement. Differential arrangement. So similarly, another plate is there. Okay, so there are two fixed plate. Okay, and another one is suppose this is a movable plate. Okay, this is a movable plate. Okay, that is actually arrangement. That is an arrangement. In case of LVDT, what you have seen. In case of LVDT, what you have seen. What is the movable part? That is the core. Core is the movable part, right? And what is the stator part? Stator part is the windings of primary, windings secondary is the stator part. That is the main part. And the movable part is the core, right? So similarly, in this case that we have arranged in this way, suppose this is two fixed plate, fixed plate, and this across this fixed plate that we will be providing some external power supply. Okay, we will be providing some external power supply across this two fixed plates. Okay, and this is your movable plate actually. Okay, this plate you have to move. You have to move up and down. Okay, this plate you have to move up and down. Okay, so in that case, suppose in that case, there is a distance. This is the distance, D. This is the distance D between it is the movable plate and fixed plate 1, and this is the another D. This is another distance between this fixed plate 2. This is fixed plate 2 and the movable plate. Okay, so there is another distance. That is a D. Okay, so now suppose this is your movable plate. So that in this that is a very basic concept that already you have studied in the electrical engineering or whatever. Okay, suppose this is your supply and there are two capacitance. Suppose there are two capacitances is there, C1 and there is a C2. C1 and C2, this is a supply. So now suppose this is your C1, this is your C1, this is your C2. Okay, so now if we want to measure voltage across this C1, okay, so this is your suppose external supply, suppose this is your E, so this is your E, okay, external supply. So if you now want to measure the voltage across C1, so what will be the formula? Voltage across C1 means E into C2 divided by C1 plus C2. Similarly, in the voltage across the C2. So C2 means that we can write that E into that is C1 divided by C1 plus C2. Okay. So same same method that we are applying, we will apply here in this differential arrangement. Same principles. Okay. So now here actually suppose consider this is a movable plate, and movable plate suppose first condition is that initial condition. Initial condition is this x equals to 0. X equals to 0 means there is no deflection. Means we are not moving. Okay, we are not moving this plate anyway. We are not moving. This is movable plate is fixed. Okay, fixed. That means x equals to 0. That means no no deflection. No deflection of the moving plate. So then what will happen? In this case, what will happen? The obviously the capacitance capacitance across this one and capacitance across this one will remain same. Capacitance across this one and capacitance across this one will remain same. Okay, so obviously the same thing like so LVDT also. So you will be getting output voltage, main output voltage, that is E1 minus E2. Suppose voltage across this plate E1. Suppose this is your E1. Okay, this is your E1. Voltage across plate this one, and voltage across plate this is your E2. This is your E2. Okay, so E1 minus E2 equals to 0. E1 minus E2 equals to 0 because the capacitance will remain same. So if we calculate in this way E1 and E2, so obviously it will become, suppose E1 equals to E by 2, and suppose this is your E, E1 equals to E by 2, and E2 equals to also E by 2. So U1 minus C2 equals to what? U1 minus C2 equals to, that is 0. U1 minus C2 equals to 0 because X equals to 0. No deflection, no deflection. Okay. Now the second point. Come to the second point. Like LVDT also. Like LVDT, what you have done? We have moved the code in the left and right or up and down, whatever you can move. Similarly, now if we give some deflection in the movable plate, suppose it is moved. Suppose it is moved in this distance. Suppose it is moved in this distance. Okay, in this distance. Suppose this now the movable plate is placed here. Movable plate placed here in this place. Okay. So now what will be the effect? What will be the effect of the distance between these two plates? Between these two plates. What will be the distance? What will be the distance? Distance क्या होगा? ये भी distance कितना होगा? Distance क्या होगा? D minus x because ये decrease हो जा रहा है यहाँ पे because total distance D. Total distance क्या था मेरा? Initial condition. Across this plate on C1, okay, and voltage across this plate C2. So that means you have to find out first E1 and you have to find out that is E2. You have to find out E1 and you have to find out E2. So what will be the value of E1? What will be the value of E1? You can calculate by yourself. That is E1 equals to what? E1 equals to what? E1 equals to, you know that E, this will be external main power supply, E into multiplied by what? That is C2 divided by C1 plus C2. C2 divided by C1 plus C2. Okay. So if we put the value of C2 and C1 in that equation, then you can find out the value of E1. You can find out the value of E1. So similarly that you can find out the value of E2. So what will be the value of E2? E2 means what? E2 means that is E into just opposite, that is C1 divided by C1 plus C2. Okay, that is the E1. So similarly that you can calculate the value of E2. So E2 means what? That is E into C1 by C1 plus C2. So you have got some value. Now what? Now you have to calculate the output voltage. So that is equals to E. E equals to output by E0. E0, that is equals to what? That is equals to E2 minus E1. E2 minus E1. Okay, so if we got some E1 minus E2 or E2 minus E1, so that is a differential arrangement, differential output voltage. So if we calculate, you have to calculate by yourself. Okay, you have to calculate by yourself. Then you can see there, you can see there is a you can establish a relation. Okay, from that equation you can establish a relation between the output voltage and this displacement. Okay, but between the output voltage E0 and the displacement X. Okay, so you can establish, you can establish the relation. Okay, after calculating this net output voltage E0 equals to E2 minus E1, then you can establish the relation between the E0 and X. Okay, so you can decide that it will be showing the linear response or it will be showing that calculate by yourself that equation. Okay, you have to calculate the equation. You have to calculate that equation by yourself. You have to calculate it. Okay, that is E equals to E1 minus E2 or E2 minus E1. Okay, after the calculation that you can find a relationship. Okay, between the change in output voltage, net voltage, and the change in displacement. So you can establish, you can analyze that it will be showing that is a linear or it is a non-linear. Okay, understood the basic working of capacitor transducers? Understood? Understood the basic working of capacitor transducers?
Yes, sir.
This is a very simple working, that because in this day after tomorrow, you will be performing the experiment of liquid level measurements in the capacitor transducers. Okay, so it is a very simple construction, very simple working. Okay, very simple working. This differential arrangement is very, very important. You may face the numerical problem in exam also. This is actually practical setup, like LVDT. There is like LVDT. In case of LVDT that we have varied, the code. So in that case, in the capacitive transducers, we have varied here the movable plate. The plate is the moving. That is the movable plate. Okay. So across that fixed plate, across the fixed plate that we have giving some power supply. So accordingly, that we will be here also considering the two conditions. One is that primary condition. Primary condition means that is the when the plate movable plate that is the fixed means no deflection. So in that case, what will be the value of the output voltage? Obviously, that will be 0. So in the second case, secondary condition, that you have to vary, you have to move the movable plate up and down or left and right. Okay, so then accordingly that you can be calculating the output voltages. Okay, so obviously this is also transducer because the change in displacement converted to change in output voltages. So that is the main working of the capacitive transducer. So this is a capacitive, very important topic. So these are three examples. Ability, arbitrary, and capacitive transducer. These are three examples of the displacement transducer. Okay. So there are very advantages, disadvantages. Uses there because capacitive transducer is very sensitive. Good frequency response. When we use for the dynamic studies, are advantages. Disadvantages. That metallic parts there is requires some insulations. Okay. So sometimes that it shows the nonlinear behavior. Yeah, that is disadvantage. You have already seen. You have already seen the two characteristics from the equation. C equal to epsilon A by D. So C proportional to epsilon, C proportional to A. So this is the advantage. So change in developing area, change in permittivity, dielectric media. So change in capacitance, that is proportional to, means change in increases. Okay, so there is a linear relationship. So somehow that it shows the non-linear relationship also. Non-linear relationship, some varying the distance between the plates, so it will provide some non-linear behaviors also. So that is the disadvantages. Okay, so these are the disadvantages. Advantages, applications, that it is used for the linear measurements because we are varying the linear. There is a linear displacement. So like that LVT, that is the one classification. That is I've shown the arbitrary. Arbitrary is the rotary. Rotary means the angular displacement. So similarly, in case of the capacitive transducers, that we can design in the angular. We can design the arrangement to provide some angular displacement, to indicate some angular displacement. Angular nothing but a circular manner that to flex the movable plate. Design something is something different. Will be something different of the movable plate, and it will be moved in a circular way. Okay, so there is angular displacement. Okay, so we can design. So most of the cases, that is for the simplicity purpose. For simplicity purpose, the linear arrangement preferred. Mostly preferred linear arrangement. Okay, like LVT also. Okay, not RVT is not preferred mostly. Okay, so that is the used for the measurement of force and pressure. Obviously, you can measure the force and pressure. Force and pressure. हम जब there I apply कर रहा हूँ force and pressure. So some object causes some displacement. Okay, so that will changes the capacitance. So that you can measure actually. You can calibrate the force and pressure also. Okay, in terms of input quantity, you can calibrate also in the terms of force and pressure. Because the first converted to displacement. Then displacement changes to capacitance. Displacement changes to capacitance. So that is the LVT. The capacitance. There is we can apply. Or you can extend the technique we can apply in the extensive version actually. In the extensive version means applications. Suppose in case of pressure sensors, some displacement sensors. So you can include any transducers to measure, to calibrate in any input quantities. Okay. Suppose in case of boron tube, you can pressure sensors, apply here the capacitor transducer, you can apply your weight transducers. Okay, according to our measure, based on our requirement, based on our measurements, based on what we require actually. Okay, suppose we want to measure some input quantity in terms of capacitance, we can calibrate in terms of capacitance, whatever. Okay, so you can include. It is possible. It is possible everywhere. Okay, so that is actually the project. There is a project. Okay, so you can continue the project after completion the course, then you can continue this type of project. Okay, so basically it will be possible in the hardware. It is not possible in the software. It's hardware. So you can do so many projects. You are dealing with the capacitive transducers, calibrated transducers. So you can apply with anyone. Okay, so to measure, indicate the displacement, the temperature, force, pressure, you can calibrate anything. Okay, so that is actually advantages. Okay, so this is another uses. That is that is humidity, that is measured also through capacity transducers. This transducer uses the mechanical modifier for measuring, the volume, density, weight, and so many applications, so many uses for the capacity transducers. Okay, you can measure, for the pressure measurement, force measurement, so whatever, accelerations, whatever the capacity transducer you can be used. Okay, like I did. So these are the basic advantages, disadvantages, and uses of the capacity transducers. And this is the basic working that I have explained already. I hope that all of you you have understood. Is it clear to all? Is it clear to all the working of capacity transducers, differential arrangement? Is it clear? Is it clear to all? If all of you have understood? All of you have understood the basic working?
Yes, sir.
Okay. So it is your task. That task is that you have to calculate the net output voltage. Okay, through that equation. You have to calculate the net output voltage through that equation. Okay, and you have to check the relationship between the output voltage and the displacement. You have to check the relationship between the output voltage and the displacement. Okay, so what will be getting? Okay, so accordingly then you can plot. Okay, you can plot the change in output voltage and change in displacement. Okay, through that equation, differential arrangement. Fine. So so this is all about the capacitive transducers. Next day that we will be performing the experiments. Okay, on the capacitive transducers. There is some experiment, liquid level measurements. Some tank will be there, and we will fill some liquid. Capacitive transducer already placed in the inside the tank. Okay, so that one wall of the tank that will be acting as the conductive medium, and because that is already capacitance internally mounted with the wall, and another plate there is a charging plate. So when the liquid level increases between these two plates, when this liquid level increases, then what will happen? That you have to notice the changing capacitance value, and accordingly that you have to calculate the output voltages. So in that case, you have to change different dielectric medium, because some water will have some one dielectric medium. If we put some another samples, there will be some another dielectric medium. Okay, so you have to check, you have to analyze the different capacitance value output voltage based on different surfaces. Okay, different surfaces. So that is will be the experiments. That is the experiment we will be performing in the next day. Okay. So this is all about the capacitive transducers, and I will share the materials of LVDT. I did not share, but I will share the LVDT and with the capacitive transducer study materials. Okay, and the slides also I will share with you. And if you have noted the equation, during my explanation, so I advise you to calculate the net output voltage. Okay, you have noted the equation. Have you noted that equation? C equals to. Have you noted that equation? What I've said, in the explanation. You have noted that equation C1 and C2 epsilon 1 epsilon E2 E1 E2. Huh? Yes or no? You have noted that equation.
Yes.
Okay. Then fine. I will also forward. I will share. No issue. But if you have noted, so please try to calculate. The net output voltages. Okay, what I've said. That is U1 minus U2 E2 minus U1, and check net output relationship between the net output voltage and the displacement. That is a very important setup. It is an important topic. That is differential arrangement. I will show you one numerical also. One example, numerical capacitive transducers. Okay, and I will give some 2-3 numericals also that will be you can practice for that. Okay, so